Okay, let's briefly do some function composition. You said you feel good with it, so let's just go ahead and do it. I'm going to define a new function. H of x is equal to, how about g of f of x? So in other words, we're taking some input value. We're first going to put it into f, and then we'll get an output. Then we're going to take whatever that output is and throw it into g of x. And so I'm just going to kind of trace my way through and say, okay, if I took an x, I would first put it into f. And f would tell me, okay, that is what pops out. Okay, so I would have a 2x. So for instance, if I put in a 3, this would say take 3 and multiply it by 2. Now you have a 6. Okay, so 6 is my output. That's the value that I'm throwing into g. And g says take whatever output you had, in our case was 6, and add 1 to it. Okay, so I should get a 7. But in symbols, what that means is g says you take whatever your input is, my input is a 2x, and then you add a 1 to it. Okay, so I add a 1. Now I'm just going to check. I plugged in a 3, multiplied it by 2 gave me 6, add 1 gave me 7. And is that what we get with h of x? If I plugged in a 3, this would say take 2, plug 3 in here, and yeah, in fact, this is almost trivial, right? And we could see like everything I just talked through. It says do this first. In other words, do that first, then do the g part, right? First multiply 2, then add 1, and we get that guy right there. Okay, that's the first function we're going to play with. The second function we're going to play with is, let's call it h. I don't want to call it j. Let's call it big capital F. Big capital F of x is going to be, well, this in the opposite order. We're going to say take g and then put him into f. So it'll be f of g of x. Like that. So in other words, do this first, then whatever you get as an output of that, which is plus 1, then put that into f of x and see what we get. Okay, so g of x. So again, looking into x, the rule says plug it into g and you get some output called g of x. That g of x is the same thing as that. So that's x plus 1. So then it says to do f to it. So we take whatever that input is and plug it into f. F says you take 2 and multiply by whatever that input is. If there was a smiley face in there, we would take 2 times smiley face. If it were a 45, we take 2 times 45. In this case, parentheses are our best friend, and they're our best friend in this class. So we want to take x plus 1 and multiply that entire thing by 2. Okay, technically we're done, but I'm going to simplify this a little bit. I'm going to distribute the 2 into there. We get 2 times x is 2x. 2 times 1 is 2. And so we can see, yeah, we get different values. Okay. Now, let's just think about this. And I want to do the same kind of thing I did before. If I plugged in a 3, this says first take 3 and add 1. G says do that first. Take your 3 and add 1. Okay, 4. Then it says take that, whatever you get as an output, and then put it into F. It says you take that number, in our case 4, multiply it by 2, and you should get an 8. Okay, is that what this says to do? Let's just check. F of 3, no, what did I plug in? 3? Yeah, 3. This says, okay, I do this right here. Plug in a 3 into here, I get a 3. 2 times 3 is 6. 6 plus 2 is indeed 8. Okay, and we can see that these are not the same thing. And in general, that's not that it's going to be the case that it's not necessarily the case that f of g of x is the same thing as g of f of x. So it's just something to know. Okay, so just quick review of composition of functions. That's how we do it. Now, what I'm interested in today is finding inverses, which we've done before, but we're going to notice something about inverses. So, okay, let's look at h of x. H of x is 2x plus 1, and as a matter of fact, that's just a line, so we know how to graph that. We could say, okay, if we had some coordinate axes, this. My x's are my inputs, and we'll call my outputs y. And I wanted to graph the function h. I would say, well, when I pull in a 0, I get out a 1. So it goes through here. 1. And then it has a positive slope of 2. And so it should look something like this. And indeed, if I were so inclined, since I'm graphing, I might as well do it. Say, when the output is 0, when the y value is 0, in other words, when the y value or the output is equal to 0, it's the same as this right here, then we could say, okay, so then what is that x value? So I'm going to subtract 1 from both sides. I get minus 1 equals 2x, divide by 2. And I get that x is equal to negative 1/2. And that makes sense with the picture that I've drawn. Negative 1/2 is on that side right there. And so, okay, now let's think about this. So an inverse, right? We're thinking about, I want to take, if I take some x input and I plug it in, I get some output value. We're going to call it h of x. Okay. And well, that thing we could call, it's on the y-axis. We might as well call it y. And so if I wanted to find the inverse of h of x, it's, we have an output and we want the original input back. So I say, okay, given that we have an output, we're calling it y. That was the output of this function. That means, okay, then y is equal to 2x plus 1 for some input. So I'm going to, I guess, I want to get x by itself, because that is the question, right? Given some value of y, we want to know what was the x. So we want to get that x by itself. So that's what I'm going to do. I'm going to say minus 1 from both sides. Y minus 1 equals 2x. Divide both sides by 2, and that should give me, and I'm going to write it like this, where I divide the whole thing by 2. And that gives me that x, the original input, is equal to the output minus 1 all divided by 2. In fact, I think this was one that we did last time. So now we have an inverse relationship, and I just want to check it. H inverse of y is equal to y minus 1 all over 2. Now let's just check a point. Let's plug in a 3 for x. Okay, so I'm plugging in a 3 into the original function h. Okay, h of 3 says, okay, we go 2 times 3 plus 1. That's 6 plus 1 is 7. Okay, so then when 3 is the input, the output is 7. Now let's just check our formula here. This says h inverse of 7 should be, okay, I'm going to replace the y with a 7 right here. I get 7 minus 1 over 2. 7 minus 1 is 6 over 2 is indeed 3. A couple things I want to notice here is H says do F first, then do G, right? So, and is that what we see? Yeah. F says multiply by 2. That's the first thing we did. We multiplied X by 2. Then we did G. G says add 1. Then we add 1. That gives us 6 plus 1 is 7. The inverse is the same thing, but in opposite order, right? So the opposite of plus 1 was minus 1. And indeed, that's the first thing it tells us to do. Minus 1 first, then take that and divide it by 2, which is the opposite of that. So this says, we'll say, put on your socks, then put on your shoes, right? Put on your socks, then put on your shoes. To undo it, we first take off our shoes, then we take off our socks. Okay, so this right now is review. I think I probably said all of this before. This is the new stuff. This is now what we're about to say is this. This is the new stuff. So we have a function h, which tells me what to do with any input. The inverse function tells me how to get back to where we came from, right? So it should be the case that if I take this output right here and put it into here, I should end up right where I started, right? Does that make sense? Like, I take any value, as we just saw that, right? You take 3, put it into the function, you get out a 7. Take 7, that output, put it back into the, or put it into the inverse, and you should come back to right where you started at 3, which is what we saw. Now in symbols, what that is we said, plug it in X, you get out something called H of X, and then you take that, whatever that output is, plug it in. So instead of calling it Y, let's just call it H of X. You should come back to where you started, which in this case was X. So let's just look at this as symbols here, right? You take some value of X and plug it into H. That gives you some output, call it Y. But then when you pull it back, right? When you say, well, hey, where did you come from? You should end up where you started off. In other words, you should end up at this same place. If I plug in a 3, I should get back a 3, right? If I plugged in a -2, well, it would tell me to do something and go here, and then we pull it back, it should bring me back to -2. If I plug in an X, push it forward, and then pull it back, I should end up where I started. So now let's check that. And this is something you want to do. Like if I say find the inverse of a function, a way, and you have some formula for it, a way that you could check that this works is just plug the original function into the inverse. And it should, you should end up where you start. In other words, for any function, when you do this, plug in an X, push it forward with H, then pull it back with H inverse, right? Plug in X, push it forward with H, pull it back with the inverse, you should end up where you start. That should be an X. Let's check. H inverse of H of X says that thing right there is 2x plus 1. Okay. H inverse says you take whatever that input is. So I'm just going to write it like this. Go -1 over 2. Right? Because I'm looking at my definition of H inverse, and I'm seeing whatever goes in there needs to go in there. If I put a smiley face in there, a smiley face goes right there. And so I'm just saying whatever goes in here has to go in here. And now we get 2x plus 1. And now I think, okay, 2x plus 1 is just 2x plus 1. I don't have to square it or anything like that. So I could drop the parentheses. I get 2x plus 1 minus 1 in the numerator. Still divide by 2 in the denominator. The plus 1 and the minus 1. Well, plus 1 minus 1 is 0. And so that's just a big fat 0 up there. 2x plus 0, which I'm not even going to write. 2x divided by 2 is x. And yes, indeed, this checks. This is a valid inverse. And again, right, we could think about, well, if you had taken a real number, like an actual number like 3, you push it forward and you get 7. If I plugged a 3 in here, this whole thing would be 7. 2 times 3 is 6 plus 1 is 7. That would be a big fat 7 right there. Then this says, take 7 and subtract 1. Yeah, you'd get 6. Divide by 2. And 6 divided by 2 is 3. Yeah, we'd end up right where we started. Does that make sense?
I think so. Maybe.
So, yeah. Okay.
I think I'm following. It's just a little bit.
It's a little abstract. It's, we're talking, take any input, blah, 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 and you come back to where you start from. It's tricky stuff, right? But yeah, so let's do this. Let's do it like this. Hi, buddy. Okay. In fact, we're gonna forget about big F right now. I need a bit more. So we plug in a 3 into this function right here. Oh, buddy, what do you need? Oh, we had inverse. Each inverse of y minus 1 all over 2. All right. So we have a function. We have an input. We're plugging in a 3 into h. H says, take your input, multiply it by 2, which is what we do first. That gives me a 6. Then it says we add a 1. Again, we think about this. This is a composition of functions. Don't worry so much about the composition right now. Like I just kind of wanted to lead into this idea of inverses here. And so, okay, we end up getting out a 7. So when 3 is my input, 7 is my output. Now, without thinking about the actual formula for an inverse, let's just think about how we defined inverse in the first place. We said an inverse is the thing that tells you where you came from, right? Remember when we were playing this game, we said A goes to 1. This is our function f. B goes to 2. And I said, what's f inverse of 3? You said, what was it?
C.
Say again? You kind of cut out. I'm assuming you said C, the letter C, right? Yeah, okay. Yeah, you cut out right there. But yeah, right, we're just saying, where did it come from? Right? So what this says is you plugged in some number and you got out a 7. And we could tell by the formula, well, it is the case that when you plug in a 3, you get out a 7. In other words, 3 gets mapped by H to 7. Okay. And so we would say then the inverse of 7 is 3. We're just saying you plugged in some number, you got some output, and the thing that you got was the thing that you started off with was a 3. So a way that we could check our inverse to see if it's truly an inverse is if we took every single number and checked it individually. We said, well, what if you plugged in a 2? 2 times 2 is 4 plus 1 is 5, so my output would be 5. And then we'd say, well, then what's H inverse of 5? Does it indeed come from 2? And then we'd pull it back and see like, well, yeah, let's just see. Plug in a 5. 5 minus 1 is 4. 4 divided by 2 is 2. And yes, indeed, you get a 2. And we keep going, right? And we just plug in every number and get every output and blah, blah, blah. And then, but the thing is, I don't have infinite time, right? I don't want to have to plug in every single number and check every single output to see if my inverse works. So what I'm going to do is be a little tricky. I'm going to be mathematical here and say, I don't have time to check every input, but if I pick any input and we just call it X, and that's what I'm doing right here. I'm saying, you know what? Instead of, I tried it with 3, I got out a 7, and then I pulled it back and made sure I got a 3. Okay, I tried it with 2, I put it in, got a 5, then I put in a 5 and made sure I ended up back at 2. Let's just, instead of picking particular numbers, let's just try an X. And that way we'll know, like, yeah, you could have replaced that X with a whatever, but when you push it forward, you'll get some output. And then what we're going to do is just pull that output back and make sure that we end up where we started here at X. So that's what we're doing. It's just symbolic. So rather than plugging in infinitely many inputs, finding their individual outputs, pulling each one of them back and checking every single case to see if it works, I'm saying, what did we just do here? I took a number 3, plugged it in, got a number out 7, and then I took that number, pulled it back, and made sure that it went to the original number. So that's what we're going to do with X. The only problem is X could be 3, it could be 2, it could be -5, it could be 703. But what we're going to do is just do it symbolically and make sure that we end up where we started. In fact, I don't have to call it X because that could be a little confusing because we have an X here, we have an X, we have our X axis. We could do it with any number. Why don't we call that number A? We'll just say A. So if I take that number A, the same way I took 3 and plugged it in, the same way I took 2 and plugged it in, we could say, well, f of A goes to, well, I don't know, what is it? Well, whatever h of A is. Let's find out what h of A is. So I take h, plug in an A, it says to take 2 times whatever A is. Then I add a 1, okay? And so then that is what that height is right there. It says that we did 2 times whatever A was plus 1. That's that height. And what I want to make sure of is, okay, we did that. So in other words, like we took a 3, multiply that by 2, add 1, we got a 7. Took a 2, multiply by 2, add 1, we got a 5. Now we're taking an A, general old A, we multiply by 2, add 1, and now we have some output value. And what we want to do is say, is this thing accurate? Well, if it is, if it's accurate, if it truly gives me back everything, like we saw that it was the case with 7, I plug in a 7, and 7 minus 1 is 6, divided by 2 is 3. Yeah, 7 does come back to 3, so that's good. It works with 5 because when 5 is the output, I plug in a 5. 5 minus 1 is 4, divided by 2 is 2. And so, yeah, it does work with 5 and 2. What about A? I don't know. Plug in an A, what do we get? Well, 2 times A plus 1. Okay, so let's take that output right there, this guy, whatever he is, and pull him back. And so I'd say, okay, the inverse of that number is 2A plus 1. And then, well, that says to, okay, we take whatever output it was, minus 1. So the output was this guy, minus 1. And then we divide by 2. So 2a plus 1 minus 1. And it's kind of like we had 7. Minus 1 brought us back to 6, right? And that's kind of what we're seeing here. So 2a minus 1 plus 1 is just 2a over 2. 2 divided by 2 does give me a. So see what we did. First we took a, plugged it into the function and got that was the output. And then we said that whenever you take that very output and do the inverse to him, you should end up right back where you started here at A. And so in symbols then, so now does that make sense that that's what we're doing? We're just checking that you take an input, do your function to it, and then when you undo that, you should end up where you started. Does that make sense?
Yes.
Right. And so now what we want to do is instead of checking infinitely many inputs, we could just say, well, let's just give that input a symbol. We'll just call it A, and we'll push it forward. And then we'll use our formula, the inverse, to pull it back. And we should end up where we started. The same way as when I put in a 3, got out of 7. Then I pulled back the 7 and got a 3, right? I put my 7 into the inverse function and ended up where I started off. Same thing with 2, plug in a 2, we get out a 5. Plug the 5 into the inverse function, brings us back to 2. Now I'm plugging in an A. It tells me to do something to A and I get some output, whatever it happens to be. But if I take that very output and pull it back, then I should end up where I started here at A. The conceptual leap here is to say, well, this symbol means the same thing as H of A. This is just an explicit formula for the output. So what I'm going to do is take that and replace it with the symbol for it, which is H of A. Let's say, okay, the output is equal to H of A, whatever that happens to be. It's, the formula, but yeah. And so now this is what we're saying in symbols, is that if you push something forward, take any value, and I hope you've kind of caught on to how I'm using this terminology. Push forward means we're putting it into the function and evaluating the output. Pull back means we're doing the inverse of that and coming back to where we started. So you take any input value, call it A, push it forward. Then when you take whatever you got and pull it back, you should be where you started off. And so so this is just a fancy way of saying, if you'll notice, like this should be true for any function. We happen to have a nifty formula, and it happened to be a line, which we feel good about. But if H is any function, it's going to have one and only one output. And so then when we take that output and pull it back, it should at least it should take us back to where we started. What we're going to see when we start talking about parabolas is it's not necessarily going to just be that. It might be a bit more than that. But what I want to introduce right now is that this is a way that you could check if you're unsure about your formula for the inverse. You could check it by plugging the function into the inverse and making sure that you end up where you started. Similarly, we could play the other game. We could say, what happens if you compose it the other way? That is, what if you started here on the y-axis? What if you took any number here on the y-axis? Like we could have just said, well, forget about the original thing. What if we started at 7 and I plugged it into there? What would I get? Well, if you started at 7 and plugged it into there, you'd have 7 minus 1 is 6, divided by 2 is 3. And so if you started at 7 and then used the inverse, you'd end up at 3. And then we could say, well, if you're at 3 and you put it into the original function, do you go back to where you started? And yeah, you would. You take the 3, plug it into there, and you should end up back where you started there on the y-axis. And so when you compose an inverse in the other way, it should also work. What I'm saying in symbols here is you do the inverse to some number, let's call it y. So there's my y. I'm going to get rid of what's down here right now. I take my y and I pull it back with the inverse. Say, where did y come from? And what we get is some, well, you know, it looks like this. It's this value, whatever it happens to be. If y was 7, it would have pulled back a 3. If y was 5, it would have pulled back a 2. If y is, and now we're just going to say, well, instead of checking infinitely many outputs, let's just call that output y, and we'll plug it into here. And what's going to come back is the number y minus 1 over 2. And then we could check and say, well, that's what that is, right? That's the green part right here. We could say, well, let's take that and push it forward with the original function. We could say, yeah, we'll plug that into our original function. And that output, well, it should be where we started off, right? It should be, if I plug that in, I get the original thing that we started with back. And so in symbols, let's just check that real quick. Or rather, this is what it means in symbols. And so let's just read this, right? We read from the inside. Y. Okay, where's y? Well, right there. There's y. It's an output. And if we take that output and pull it back, it tells me what input that is. That thing right there, y minus 1 over 2, is that right there, all that in green, h inverse of y. Now we're at some point on the x-axis. And if I take that point on the x-axis and plug it back into the original function, it's going to say, well, just go back to where you came from. Go right back to y, right? And so that's what I'm going to check right now. I'm going to erase this stuff right here. And say, okay, I have h of h inverse of y, h of h inverse of some number y. H inverse of some number y, oh, that's right, that's that function right there. And so I have h of y minus 1 all over 2. Okay. H says, take whatever your input is, multiply that guy by 2, and then add 1. So right now, I'm not really looking at what is in there. I'm just saying, okay, h of any number says take that number, multiply it by 2, and then add 1. So that's what I'm going to do. I'm going to take that number, plug him in, 2, then we plus 1. Let's see what happens. I guess we have a 2 divided by a 2. Like if we wanted to, we could say that's the same thing as 2y minus 1 all over 2. Think about it like that. But I can see that, yeah, this is just undoes the division. I mean, it undoes the multiplication here by 2 undoes that division right there. Those two numbers cancel. And I'm left with just a y minus 1 right there, y minus 1. Then it says take that and plus 1, minus 1 plus 1 gives me this back right there. So now I can see that, yeah, no matter what number I plug in other words, no matter where I start, if I put him into the inverse function, going back, we'll get some value here. Take that value and put him back into the function, and we should end up where we started. So for instance, take a 7 and pull it back. 7 minus 1 is 6. Then divide by 2 gives me 3. Plug a 3 into H, and it says take 2 times 3 is 6, plus 1 is 7, and I end up back at 7. But instead of checking infinitely many points, I'm going to say, well, instead of 7, what if I just started at, say, Y, or Y is any output? Well, then what? Well, this is what would happen. You would have taken your Y, subtracted 1, and then divided by 2. Then you'd push him forward, take whatever number that is, and multiply it by 2. Oh, that undoes the divide by 2. And then you would add 1. Oh, that undoes the minus 1. And you should end up right where you started. Now, this nifty little formula right here will work for any function. And this is a brilliant way to check that your inverses work. The other one, we haven't even talked about it yet, and we're not going to until we really get into parabolas. But this one, where you do the function first, and then you pull it back, it should give you your x back, but it might give you more back. We'll get into that later. That's not really the point. But what I wanted to show you is because this is a nice way to tie it, or I think kind of round this off. We talked about composition of functions. We've talked about the inverse of functions. So what happens when you compose inverses with themselves? Well, it's like you come back to where you start, right? This, I start at 2, it tells me to go to 5. And then if I then take that and put it into the inverse, it tells me to go back to where you came from. That's kind of what we're saying in symbols right here. Does that make more sense?
I'm tracking.
Yeah, this is wicked stuff. And you're gonna if you go and take analysis, like a 300 level class in mathematics, this is like one of the things you start off with, and it takes a long time to let it seep into your head. So, and I'm not just like trying to blow your mind or anything. It's like, this is going to become really important when we talk about exponential functions and logarithms, like really important. And most people, and like, in fact, all the people that I've ever tutored who have problems with logarithms and exponential functions, it's because of this principle right here. It's because this principle never really took root. And so it's real important to get into this. But practically, this is nice. Like if you have a formula for an inverse function and you plug it into your original function, you should get back what you started with. So it's a nice way of checking that you have a good formula. And so if you say on a quiz or something, you write down, this is the inverse of this, and you want to make sure that that's the case, you could plop one into the other and make sure that you end up where you started. So we'll see this, well, we're definitely going to see it again when we talk about exponential functions and logarithms. Yeah. So, okay, that's pretty much all I wanted to say on that, and we've already run over. Do you have a few minutes? Because I'd like to just quickly, whatever that means for me, quickly talk about perpendicular slopes.
Yes, I have a few minutes.
Okay, cool, great. Okay, so getting this out of the way. Your book gives a proof for the formula for a perpendicular slope, and I hate it. I hate it. What we're going to do is think about any line at all, and let's say it looks like this. It doesn't matter that it is a positive slope right now. I've drawn it with a positive slope because it's easier that way. We could have started with it being a negative slope, but right now it's a positive slope. So it has a rise and it has a run. I'm going to start by looking at the run. And I could go anywhere on this line to start calculating it, because that's kind of how slope works. How about we'll start right here. Start at this point, and I'm going to calculate the run. I'm going to go about, I don't know, that far. And then I'm going to go up to find the rise, right? That's what rise and run are. So I'm going to go up this far to find the rise. Now, the way I like to do it, and the way that I've said before, is I just think about these as distances. I don't think about it as something minus something else first. I just think, what's the distance? Distance is always a positive number, right? And so I'm going to think about the distance first, and I'm going to say, well, this distance right here from there to there, the height, we're going to call it A. This distance from here to here, this length, I'm going to call it B. They're both positive. And in this case, A is indeed positive because it's getting bigger. So I know that when I calculate my slope, I'm going to have A be a positive number. And so, okay, if I had those numbers, I could find the slope of this line, and I would call it M. That's what we do. M is the rise over the run. And so in this case, it's going to be A, I guess, right? That's the rise, is A. Positive A, because he's going up. And B is the run. And so we have that guy right there. Okay. Okay, that's like algebra 1 stuff, right? So how do we find how do we find a perpendicular line? Well, your book just draws the picture without explaining what's going on. This is how I think about it. Get down. Thank you. So the way I think about it is, first off, the obvious things that are perpendicular here in this picture are the X and the Y axes. Like, you could almost take that as being the definition of perpendicular, saying that the way X is to Y, they're at right angles, right? That's what it means to be perpendicular. And so what I'm going to do is say, well, okay, there's something else that's also perpendicular here. And as a matter of fact, first off, what I noticed with this B is that if I were to continue this out to be a line, let's just imagine that this line just ran on forever in both directions. What's that line parallel to? It's parallel to another line I've drawn on here.
The x-axis?
The x-axis. It's parallel to the x-axis. So if I wanted to take that and make it perpendicular to the x-axis, I could take that line and rotate it up 90 degrees, right? So if I took this line right here, that red line, and I rotated it 90 degrees, say counterclockwise, then I would end up with a vertical line. And that would be parallel to the y-axis, right? Now, if I did that, now let's just imagine the picture that we have here. I have an actual length that goes from here to here. We've called that length B. If I took this line with that B drawn on it and I rotated it up, then that B would go up to about right here. And that guy, a little bit less. That guy right there would be the length B. Yeah? Does that make sense? Does that look good? Do you believe that?
Yes, that makes
Yes,
sense.
right? It does make
Yes.
sense. It looks right. Like I buy that. So then if I took this entire picture, right, and I rotated it, right, the A would be attached to it. And what's important is that that would be at a right angle to it, just by the way we've defined rise and run, right? Run is in the X direction. Rise is in the Y direction. So if I take my former run and pushed it, now it's running in the Y direction. Well, this thing would have gone over and would be sticking out now this way. Right? If I had that same little triangle that I drew, it would look like that. Maybe A is a little bit longer than that. And that length would still be A. Right? It's still the same length because I haven't changed anything. I just took the original picture that I have and I just rotated it by 90 degrees. And so now that we've seen what happens to the triangle, we can imagine what would happen to the line. The line would also be rotated exactly 90 degrees and now would go through 90-degree angle. Hi, buddy. And so I'll just kind of write this a little bit better. And so now the new line that we had, we took the old line, and remember, we took this entire picture and rotated it by 90 degrees. And so now the angle between the two B's is 90 degrees right there. Oh, buddy, you're okay. Oh, you're okay. And so then the angle between these guys would have to be 90 degrees as well. And that is what we're looking for. Okay. So that's just the picture they kind of draw. And they actually, and I think that they draw it with it this way and further up, which is like, wait, how did you get that? Well, this is how you get it. And so now we could talk about the slope of this line. Let's call that slope M2. In other words, a little subscript 2 to differentiate from the first one, which I'm going to call M1. Okay, so what we do then is say, well, what's the rise and the run? Well, the run, well, actually, let's start with the rise. It's not a rise, actually, it's a fall, right? And the way I've drawn it, I have it as B. But B is a positive number, right? By the way I defined it, I said it's just a distance. And so whatever, but now we kind of have to use our brains and say, is this a rise or a fall? And so, well, it's a fall, so it's a negative number. So I'm going to say, okay, then the rise in this case is actually a fall, and it's a fall of B units. So I'm going to call that minus B. Okay, then the run is going to be this guy right there. That's A units in the horizontal direction. So rise over run, or the fall over the run, is going to be negative B over A. And then your book does the thing that I hate. It says, okay, so we could see that M1 times M2 is negative 1. What? Well, let's just see what they're talking about here. Okay, M1 times M2 is, and they actually just show this. They say M1 is A divided by B. Okay, A divided by B. M2 is negative B divided by A. So we multiply negative B over A. So then, well, we could see, yeah, the A's cancel. So the A over A is a 1. The negative B over positive B should just stay negative, and we get a total of negative 1. And then that's where your book stops. It says M1 times M2 is -1. And then the very next thing they say is they give you a line and say, find the slope of a line perpendicular to this. And when I look at this, when I have this right here, I'm like, I don't know what you're talking about, quite frankly. So the thing to notice, though, is that how do you get from here to here? Well, you flip it, right? You interchange the A's and the B's. The rise for the old one becomes the run for the new one. The run for the old one becomes the rise for the new one, and you make the entire thing negative, right? And then, yes, it's true that if you then take those numbers and multiply them by each other, you get -1. That doesn't really tell me how to go about calculating something. So another thing we could do is we could say, well, hold up. If M1 times M2 is equal to -1, it must be the case that, well, I don't know, let's maybe divide both sides by M1. I get that my new slope, which is perpendicular to the old slope, is -1 divided by the old slope. Let's just check that real quick. We're saying you want a perpendicular slope to a slope that you already have. Then what I'm saying that you do is you take -1 and divide by the old slope. So in this case, the old slope was this. And so I'm going to say, okay, let's just check A over B. Divide by a fraction is the same thing as multiply by the reciprocal. Oh, and that's where we get that nifty little flip right there. And so we get -B over A. And yeah, that's what we get. A slope that's perpendicular to the old slope is the same thing as flipping it and making it negative. So I want to do just real quick. I know we're running way over on time, but if I would like to do some quick examples on like practically what you would do to do this. Do we have a few more minutes? Can I erase this stuff? Good. Okay. Erase. Okay. So we just said 2 ways of thinking about it. Given M equals A over B, then perpendicular to this is negative, flip it, make it negative. So let's do this. Oh, here's one way of thinking about it. Another way of thinking about it is perpendicular to this is -1 over the original slope. So when do we want to use one and when do we want to use the other? So let's do a few examples. Okay, so can you hear him?
I can. Oh my goodness.
Okay, so let's say then my slope is 2/3. What would be the perpendicular slope to 2/3?
3 over 2.
Say again?
Would that be -3 over 2?
Yes, -3 over 2. So that's when I'm going to use this rule. I see a fraction and I'm going to go, oh, flip it, just like you said, make it negative. Okay, what if I have 2? What's perpendicular to the slope of 2?
-1/2.
-1/2. Couple ways we could think about that is like 2 is equal to 2/1. So if you ever just have an integer, you could think, well, that's 2/1. If I flip that fraction, that's 1/2. Then if I make it negative, it's just -1/2. Okay. How about, what if I had -5/4? What's perpendicular to -5/4?
4/5.
Positive 4/5. Right? Because we're just we're flipping it, making it negative, making a negative is positive. Okay. What about this? Don't think too hard about this. What would be the perpendicular slope to 2.718? Do not make it a fraction, or don't, in your head, don't try to turn that into a fraction. Just do this, like, and this is the thing I'm getting at. It doesn't need to be harder than it needs to be, right? Like, if it's already in a fraction form, just flip the fraction. If it's not in a fraction form and it's not like an integer, or well, even if it is an integer, if it's not in a fraction form, don't use your brain. Just say, well, -1 divided by whatever the original slope is. If you wanted to, you could say, okay, 2.718 is the same thing as 2.718 divided by 1,000. And then, okay, we would have -1,000 over 2018. You could do that. Or you can make your life a lot easier and say, whatever number that is, if I need it to be perpendicular to that slope, I'll just take -1 and divide by the original. So, and that will be fine. That would be just fine. So if I had, I don't know, -√3, what am I going to do?
Sorry. 1/3 squared? No, wait, yes.
1/what?
3 squared?
No. 1/√3. Don't think too hard about it, right? We're not trying not to use our brain here. Right? And we want to find the perpendicular slope to it. -1 over that number. Yeah, negative, right? We're kind of thinking like, if it's not negative, make it negative. If it's negative, make it positive. We don't want to use our brains too much. Now, you've probably had it beat into your head that you never put a square root in a denominator. I don't care. Like, and when you go into trig, you're going to be putting square roots in denominators all the time. And like pretty much after this class, it won't matter. Like, if we really wanted to, we could say, yes, 1/√3. Have you rationalized denominators before? Do you know where I'm going with this? Because if not, we don't need to go there.
I have in Algebra 1 because my teacher was a crazy NASA scientist who didn't really understand that we were too young for that. So I don't remember anything.
Okay, it's fine. It's fine. Like, there's a way of doing it where they say we can never have an irrational number in the denominator. And so what we do is we multiply this guy by 1, but we write 1 in a special way. We write it as something over itself. And then the thing that turns that into a rational number is the square root of 3. Square root of any number times itself, the square root of it, is the thing that makes that number pop out. So we do that, but we say, well, we can't change the value of the number, so we multiply by √3 over itself. And so then we get the square root of 3 over 3. And that, so we could, if we wanted to, I don't want to do this, but we could write that as the square root of 3 over 3. I wanted to throw you a curveball because and I wanted to throw you a couple curveballs to really get it. So, but sorry, I didn't get to my point. I don't care about this. I don't care about that because as soon as you take trig, you're going to be putting square roots in denominators and nobody cares. Like that's just the way we do it. So anyway, I wanted to throw you a couple curveballs because I don't want this to be harder than it needs to be. If it's not a fraction, right? Fractions are easy. You just flip the fraction and make it negative. Flip the fraction and flip the sign, basically. If it's not a fraction, don't worry, just go -1 divided by the original slope. So if we have a line, like in this case, if we had a line that was y equals -5/4 x plus 3, and we wanted the slope of the perpendicular line, we would say then the slope of the perpendicular line that we want is, you flip the fraction, make it positive in this case. If you had something weird like 2.718x plus 3.01, and we needed a perpendicular line to that, you might go, wait, what? How do I? Don't use your brain. Don't use your brain. That's what I'm saying. Like we've already done the hard work. Like we have this. We know that we could just take -1 over the slope that you want right there. That would be the slope that's perpendicular to this guy. Even if it's something like this, even if it's like square root of something, right? Or like 10 to the 10, you just take whatever number it is, put it in the denominator and put a little negative in front of it. So we good there?
Yes.
Cool. Okay. So, okay. Next time, I do want to start talking about systems of equations. I want you to get some practice with like something like this. Like, I'm just going to go ahead and make this. Here's homework. Find the equation of a line perpendicular to the line. Now let's do, we're going to have 3 problems. 1, 2, 3. Perpendicular to the line. In the first case, it's the line 2x plus 3y equals 5. The next line is going to be, how about y equals -2x plus 3. And the final one is going to be different. How about 7x minus 2y equals 1. So this is, instead of writing this 3 times, right, just plug this in and going through the point. In the first case, we're going to go through the point 1, 1. In the second case, we're going to go through the point 2, 3. In the last case, and these are, because I'm just pulling this right out of the top of my brain, you can expect these to be ugly, but they're going to be fractions, and you could deal with fractions. That's fine. Okay. So how about 1? How about 3, 4? Okay. So to be clear, what we're saying is there's 3 problems to do. find the equation of a line. Your first problem is find the equation of a line perpendicular to this, passing through this point. Your second problem is find the equation of a line perpendicular to this line, y equals negative 2x plus 3, and going through the point 2, 3. Next equation, the third problem is find the equation of a line perpendicular to this line, going through that point right there. So write that up. Remember what we talked about in the last lecture of the easy way of doing these things. And I'm going to go ahead and give you a huge hint. The very first thing you should do is write down, okay, what do I want? And then ask yourself, and then remember, oh, there's two numbers I need to solve this problem. There's this number right here, and there's this number right here. And in each one of these cases, one of those numbers is going to be right there. And then we could remember there's a pretty easy way of doing this without doing anything else. So this should be a pretty easy one.